Welcome, everyone. Thank you very much for taking the time to attend this talk. So in this project on multidimensional screening, bio-optimal learning, and informational robustness, well, first and foremost, this is joint work with Rahul, my colleague here at Toronto. So the title basically says it all. We look at multidimensional screening and combine it with bio-optimal learning. Multidimensional screening is a traditional mechanism design problem asking the question, well, how should we optimally sell multiple goods to a single buyer? This is a classic economic problem that is notoriously intractable. Now, buyer learning, basically, if you think about a trading environment, buyers can learn about product values before trading, and it makes sense to think that how buyers learn will influence the outcome and also the optimal mechanism that a seller should choose. So in this project, we ask, well, what can we say about multidimensional pricing if we include buyer learning into the problem? Just to give you a rough idea about what we're going to look at, this is a model overview. I'm going to give you the details in just a minute. So we look at a pretty standard multidimensional screening setting. So there is a seller with n goods for sale, a buyer with an n-dimensional type theta, and F is the prior distribution. The type theta is initially unknown to both the buyer and the seller. In the information stage, the buyer can learn about his type from a signal. We model this as a general signal, so flexible information acquisition here. Signal consists of a set of signal realizations S and a joint distribution over signals and types. And the buyer will learn by privately observing a signal realization S. The seller is the one who offers a mechanism. And then in this trading stage, the mechanism will be implemented. So the buyer chooses a report and payoffs are realized. Depending on the information environment that we look at here, the seller may either know how the buyer learns, so know this information structure of the buyer and choose a best response to it. Or the seller may be uncertain about how exactly the buyer learns and may hence want to choose a mechanism that guarantees him the highest revenue against any possible signal of the buyer. And so our aim is for these two cases to study the seller optimal mechanism under buyer learning. As a preview, we derive the seller optimal mechanism in these two distinct information environments. The first is asking the question, well, what form does screening take in the most advantageous information environment for a buyer? This is the signal and the optimal mechanism that maximize consumer surplus, where the mechanism is a best response to the signal. We term this a buyer optimal outcome. Based on the insights we gain from this setting, we then ask the question, well, how does a seller screen who doesn't have precise knowledge of how a buyer learns? In this case, if the seller is uncertain about how a buyer learns, the seller may wish to implement a mechanism that guarantees the seller the highest profit against all possible signals. And we term this an optimal informationally robust mechanism. We relate these two problems and show that in both cases, screening takes the form of pure bundling. And I'll give you details in the talk. Let me skip the literature in terms of time, but just so you see there's related literature and feel free to ask me about details here. But let me jump right into the model. So there's one seller who offers a unit of each of n goods for sale. The cost of producing a good are 0. There's one buyer with an n-dimensional type. Each dimension, each theta I is drawn from an interval, a non-negative interval. And F is the joint CDF, which is the prior distribution of the buyer's types. We assume that F allows for a positive density. Now we make one important assumption on the prior, that is some kind of a symmetry assumption. We assume that the prior is exchangeable, meaning that for any permutation, the joint distribution of the permutation is equal to the original distribution F. Okay. This does imply that we will have the same marginals in each dimension. However, it allows for both positive as well as negative correlation. We also assume that the bias type is initially unknown to both the buyer and the seller. Now, for the value function, we consider a framework that is more general than additive values, but importantly incorporates additive values, which is the common assumption made in multidimensional screening. So given a type theta, we assume that the bias value for bundle B is the sum of the bundle values multiplied by a parameter kappa B, which may be different for each of the bundles. We assume that this kappa B is non-negative for each bundle, and we normalize the kappa of the grand bundle to 1. We also assume that not obtaining any objects gives the buyer a payoff of 0. Now, we make an assumption here, weak free disposal. We assume that the value function satisfies weak free disposal. This means that regardless of the buyer's type, we assume that the greatest surplus is generated by trading the grand bundle, so all of the items. Okay. Formally, we must satisfy this inequality. Now, technically, this requires an upper bound on the kappa B for the proper subsets B. But importantly, it does not require for proper subsets that the kappa of the larger subset is actually larger than the kappa of the smaller subset. And if the lower bound of the support of our prior distribution is strictly greater than 0, then we can even have that the kappa of proper subsets of the full bundle are strictly greater than 1. Now, for buyer learning, we model this as flexible information acquisition. So the buyer learns about his type theta via a signal. Here we allow for any general signals, where S is the set of signal realization and G is a joint distribution over signal realizations and types. And we assume that the buyer privately observes a signal realization. So this will be the private information of the buyer. Now, we assume that our buyer and seller are risk neutral, and we also assume a standard kind of linear, quasi-linear environment. So without loss, we can hence restrict attention to unbiased signals. That means that a signal realization will be equal to the posterior estimate of a buyer. And so this is why we refer to the signal realizations as the buyer's posterior type. We then identify a signal with its induced distribution over posterior types, which we denote by G. And if you think about the original signal, if you look at an unbiased signal, this will just be the marginal distribution over signal realizations here. And so our calligraphic G will be what we will use to denote the set of signals here. Okay, so these will be n-dimensional signals. Now, let me tell you about how we define a mechanism. We define a mechanism completely standard. Here we look at indirect mechanisms, so we use the general form. So mechanism consists of a set of messages M, a possibly random allocation function Q, which determines the likelihood of receiving the various bundles given some report, and a transfer function, which specifies a transfer for every report of the buyer. We also impose the standard individual rationality and IC constraints. So individual rationality here means that we can't force the buyer to participate in the mechanism that will give him a negative payoff. And we also assume that the buyer chooses a reporting strategy that is the best response, meaning that so our USM will be the expected payoff of the buyer if his type is S and the mechanism is M. So in that case, his expected payoff is just the expected payoff of receiving the bundles, or he may receive different bundles in the allocation, and the expected payment given his report. And we assume that the buyer chooses a best response here. Okay. Now, given a signal G and a mechanism M and a best response sigma of the buyer, then the seller's profit is simply the expected transfers of this mechanism, okay, or of this equilibrium. All right. So let me give you an overview of our results, and let me start with the buyer optimal outcome. First of all, what exactly do we mean by a buyer optimal outcome? So we refer to a pair of a signal for the buyer and a mechanism for the seller as an outcome, when G is the signal for the buyer, M is an optimal mechanism for the seller in response to G. So M is the best response of the seller. Sorry. The goal is to characterize the buyer optimal outcome. So an optimal signal G star for the buyer and best response of the seller that maximizes the buyer surplus across all outcomes. So formally, we want to maximize the buyer's surplus. So we want to choose the signal that maximizes the buyer's surplus subject to the seller best responding to that signal. Now, in this problem, in the objective function here, this is the information design problem, which will determine the buyer signal. And then in the constraint, we have the mechanism design, the multidimensional screening problem. Okay, so this is our first main result. We show that there exists a buyer optimal outcome, so a signal for the buyer, a mechanism for the seller, such that the seller's mechanism is a pure bundling mechanism, meaning the seller offers the grand bundle, so the bundle of all items, at a fixed price. The signal of the buyer is perfectly correlated across dimensions. And the buyer is allocated the grand bundle with probability 1, so trade is efficient here. Now, let me point out some things here. So the seller uses a simple mechanism in equilibrium. So he uses simply selling the grand bundle at a fixed price, which means that this correlation in the signal reduces the seller's ability to screen, and this is beneficial for the buyer. Let me point out here that we get this perfect, that the buyer optimal signal is perfectly correlated, even, for example, if we start with IID types, with a type word which is IID. So in that case, in order to create this correlation, this perfect correlation across dimension, the only way to get that is by introducing noise in the signal, which may lead to a worse decision by the buyer, but it turns out by introducing this noise and shutting down the ability of the seller to screen, this will benefit the buyer more than making some mistakes because of the noise. In the proof, we actually construct the buyer optimal signal explicitly. We show that it's perfectly across dimensions, and there is a second type of noise in the signal which determines the shape of the signal, and which will result in the marginal distribution of this optimal signal, or the marginals being truncated Pareto distributions. Let me just make some remarks here. So in the case of additive values, it is true that separate sales is also best response. Why we frame this result as pure bundling being optimal is that this seems to be the part that is robust if we move away from the additive values case. So especially if the kappa B is strictly greater than 1 for some proper subset, one can actually show that separate sales is not a seller best response in any buyer optimal outcome. Let me also point out here that we can say something about comparative statics also for the finite case. And then an important corollary here, which will lead to the second part of our second main result, is that a buyer optimal outcome is actually the worst outcome for the seller. So formally, we can say that the seller's profit in any outcome is weakly greater than her profit pi star in any buyer optimal outcome. So pi star is hence a solution to the min-max problem. Now, let me talk about the optimal informationally robust mechanism. Recall that the buyer optimal outcome minimizes the seller's profit, and hence this pi star is a solution to the min-max problem. It is also natural to consider a max-min problem. where here the seller first picks the mechanism and then nature chooses a signal. So in this case, if, say, the seller is uncertain about how buyers learn, the seller may wish to choose a mechanism that maximizes his revenue guarantee. And we say that a mechanism M provides a revenue guarantee of pi if this mechanism gives a profit that is weakly greater than revenue pi for any signal and any possible best response of the buyer. And as I mentioned, a seller may be interested in choosing a mechanism that provides the highest revenue guarantee. And the solution to this problem can be viewed as an optimal informationally robust mechanism, because a seller who does not know how a buyer learns would wish to implement such a mechanism. Formally, we define an optimal informationally robust mechanism as a solution to the max-min problem. And we find that there is a random pure bundling mechanism that is an optimal informationally robust mechanism, and that this mechanism provides a revenue guarantee of pi star, so of the seller's revenue in the buyer optimal outcome. We obtain this result by combining our buyer optimal outcome result with insights from Du's paper. Let me just mention some implications here. So what is interesting and neat is that what we obtain here is a simple informationally robust mechanism. The seller will offer the grant bundle at a random price. We also, as a result, we also get here that the seller's revenue in the min-max and maximum problems coincide. And we see that while deriving the optimal mechanism may be prohibitively hard for fixed distribution, the informationally robust problem is generally tractable. Okay, so let me conclude just by wrap up. So we include biooptimal learning into the multidimensional screening problem. This, maybe surprisingly, makes the multidimensional pricing problem tractable. In the biooptimal outcome, the biooptimal signal introduces these two distinct types of noises, one's introducing perfect correlation, and then the other one introducing a specific shape. And it is the best response for the seller to offer a pure bundling mechanism. In the optimal informationally robust mechanism, the seller randomizes over pure bundling prices. And we also find that the solution to the min-max and maximum problem coincide. We think that our results may explain why very complex screening is seldom observed in practice, whereas we do observe pure bundling quite often, or it's commonly observed, for example, online, if you think about Spotify, Netflix, etc. Thank you.